Hey gang, welcome to Math 254 virtual mode. This is starting up in section 3.3. We're going to be doing some lecture notes via video, and we're going to see how this goes and try to do as good a job with them as we can. So we're going to start off right at the beginning. This is page 33 at the top of section 3.3. And one thing you'll notice right away is it says we're going to be taking a look at phase portraits for linear systems with real eigenvalues. The key here is we're going to be dealing with real eigenvalues. So that means lambda is an element of the real numbers. Now, as we talked about in class before break, it's possible to have eigenvalues that are things that are not real numbers, because you could have a solution to your characteristic polynomial that are complex numbers. So we're going to get to those in the next section, but this section deals only with real eigenvalues. And we're going to start off by kind of recapping where we were in chapter 2 and in just the last section as a kind of a quick reminder. If you start off with something that looks like a second order differential equation like this equation right here, we can rewrite it with a couple of assumptions. The first assumption is, and it's not written here even though it should be, it says convert this to a first order linear system. Well, this is presuming that we're dealing with a damped harmonic oscillator. And we can tell that it's damped because it has this term right there. The 3 tells us that coefficient not being 0 tells us that we're dealing with a damped harmonic oscillator. So for part A, it says you need to come up with a system of first order linear differential equations. Well, we have a second order differential equation, but the other thing that we know, and this is for part A, is we know from the start that the derivative of the position function dy dt is always going to be equal to the velocity function v. So that's the first kind of gimme equation that we can start with, presuming that we're talking about a damped harmonic oscillator. And if that's the case, then we can take this equation along with our second order equation, rewritten with a little bit of modification. We get dv dt, and that's our second derivative of position. That's dv dt right there. These other two terms are going to slide over to the other side, and that gives us a minus 2y minus 3v, because of course v is dy dt. That's the same thing as dy dt. So really this equation that we just came up with right here is just a modification of the blue boxed equation up there. They're really the same thing. But taken together, these two are the system of first order linear differential equations. And what's nice about them is that we can actually slide them into a matrix and write them as a single matrix equation. And so it would look like this: dy dt up top and dv dt down below. That's the left-hand side of our equation. So our derivative is equal to something times our variable. And in this case, the something is our coefficient matrix. And so for our coefficient matrix in my dy dt equation, I have to be careful of which column represents what variable. My coefficient matrix is going to be 2 by 2. And since I want it to be times y is the top and v is the bottom, that means that this first term right here, this first element in the matrix, needs to be my y coefficient from this equation. So that's going to be a 0 here. And then there's a 1 in front of the v, so that becomes a 1. And down here we have negative 2, because we have negative 2 times y, and then negative 3 times v. So if you do the matrix multiplication, you get 0 times y plus 1 times v. That gives you your first equation. And negative 2 times y minus 3 times v. That gives you your second equation. So this really is my matrix form for my system of linear equations. And of course, we know from playing around with this thing that what we have in this guy right here, let me get out a little bit of a highlighter here so I can see what's going on. This guy right here really is super special. That thing, that highlighter didn't work so well. I'll ignore him next time. That thing that we just highlighted, or tried to highlight, is what we call our coefficient matrix. And we learned in 3.2 and 3.1 that everything we need to know about the system of differential equations, everything we need to know about it is locked in to those four numbers right there. So part B then says, okay, compute the eigenvalues and eigenvectors for the system. So we can do that. We can play around with part B and say, in order to find our eigenvalues, we have to get our characteristic polynomial. Characteristic. And the characteristic polynomial, if you remember, involves taking a look at my coefficient matrix and writing it, or coming up with a determinant with a minus lambda in these two diagonals. So it's going to be 0 minus lambda times negative 3 minus lambda minus, and then the other diagonal multiplied together. So minus negative 2 times 1. And that's got to be equal to 0. And if we play our cards right and kind of expand this out with a little bit of algebra, we get lambda squared plus 3 lambda plus 2 after some condensing equals 0. That is what we would call our characteristic polynomial. And this thing, it just so happens, does factor. We can rewrite it as lambda plus 2 times lambda plus 1. And that's equal to 0. And the only way that can happen is if we have two possible values. Lambda 1, we'll call it, is equal to negative 2. And the other one, lambda 2, is equal to negative 1. And so those are what we call the eigenvalues. They are unique to this particular coefficient matrix. Oh, sorry, let me slide that up a little bit so we can see. They're unique to that coefficient matrix, and everything that we need to know from the coefficient matrix we can determine by finding the characteristic polynomial, getting the eigenvalues, and then using those to find the eigenvectors. And so if you remember, the process for finding the eigenvectors really takes us in kind of along two paths. One is there's an eigenvector for lambda 1, and there's an eigenvector for lambda 2. So we're going to do those in turn. Let me scoot this up. And I apologize. Every once in a while I'm kind of looking over at the screen to make sure that the paper isn't sliding too far one direction or the other. So for lambda 1 equals negative 2, we're going to take this out for a spin and say, if this thing really is an eigenvalue, then we should be able to take our coefficient matrix times this yv, that vector, the eigenvector essentially, that should be equal to the eigenvalue itself, negative 2, times that vector itself. So in written form, it's going to look like this. The coefficient matrix 0, 1, negative 2, negative 3 times some, we'll call it y1, v1, because they are attached to that particular eigenvalue. That has to be equal to the eigenvalue itself, negative 2, times that same y1, v1. Right, and so this goes right there. And of course, we're going to do the exact same thing for lambda 2. So over here, I'm going to say for lambda 2 equals negative 1. We should be able to say that same coefficient matrix, 0, 1, negative 2, negative 3, times, in this case, it would be y2, v2, should be equal to negative 1 times that eigenvector as well, y2, v2. You got to be careful with these subscripts. I can't tell you how many times I've started writing y1 over here and then y2 over there, and it gets confusing, but it's bookkeeping. It's algebra, so it's a lot of bookkeeping. So let's kind of play these out. Since this is a matrix equation, it really represents two equations. There's a top equation and a bottom equation. The top equation is 0 times y1 plus 1 v1 is equal to negative 2 y1. And there's a bottom equation. The bottom equation is negative 2y1 minus 3v1, and that's equal to negative 2v1. And you'll notice that these kind of are a pair. They're a set. They go together. And if you're going to, quote unquote, solve them, the only way that you can solve them is by finding the values that make both of them true. So with a little bit of effort, you can find out that this equation really is the same thing as up here, v equals negative 2y1, v1. And down here, with a little bit of modification, you can kind of slide the positive 3 over to the other side, and you have v1 equals negative 2y1. What do you know? It's the same thing in both cases. So this equation tells us the relationship between the vector directions y and v. And it says basically for every 1 unit that you go in the y direction, you go negative 2 in the v direction. Or another way of saying that would be my vector 1 would be equal to, for every 1 unit I go in the y direction, I go negative 2 in the v direction. There's my v1. I just found my eigenvector associated for lambda 1. And I could do the same thing here. I'm just going to convert them into equations to kind of see how they play out. There's other ways to do this, by the way. This is just the most straightforward algebraic way. So here we have in the top, we just have v2 equals negative v2. And down here we have, oh, sorry, nope, y2 up top. See, I'm already getting ahead of myself, aren't I? That's a y. Boop. There we go. And in the bottom equation, it's going to be negative 2y2 minus 3v2 equals negative v2. And both of these equations are going to tell us something. And you can probably guess, if I slide that 3 over to the other side, I wind up with positive 2v2 on this side, negative 2y2. So either way, I'm going to have the exact same equation. There's a relationship that says whenever you have v2, that's the same thing as the negative of y2. And that means my vector, my eigenvector 2, notice this is not the same thing as the velocity variable. This is not the v here. This is a vector, right? This is equal to the vector, whatever you have for y, your v is negative that. Oops, sliding around here. So we now have our eigenvalues and our eigenvectors for lambda 1 and v1, vector 1, and lambda 2 and vector 2. So that means I should be able to do, let me kind of zoom back up, part C, which is write the general solution. Because if you have both eigenvalues and both eigenvectors, then part C, the next part, is easy peasy. Part C says all you need to write the general solution is to know that the general form of the solution is a relationship. And it's going to be, I'm going to write it in vector form, so big Y of t. This is the solution matrix, is going to be equal to some constant, k1, times e to the lambda 1, negative 2, t, times the vector 1, this one here, 1, negative 2, and plus, there's another constant, times e to the lambda 2, which is negative 1, times t, times its associated vector, 1, negative 1. So this is the general solution in matrix form, as we've already written. So I'll just write off to the side, this is matrix form. But if you wanted to see it in, oh, that doesn't show up too well on the screen. Apologies. I won't use that pen again. If you wanted to see it in parametric form, you could say the top, the little y equation would be k1 e to the negative 2t times 1 plus k2 e to the negative t times 1. And then if you wanted to find the v equation, the bottom row would be k1 e to the negative 2t times negative 2 plus k2 e to the negative t times negative 1. So writing that out in all its gory detail here, right underneath here, you could say y of t and v of t are going to have together as a set here, as a parametric set. You could say this top one's just going to be simple k1 e to the negative 2t plus k2 e to the negative t, and the bottom is negative 2 k1 e to the negative 2t plus k2 e to the negative t. And so one of the things you'll probably recognize when you see it written like that, and here I'll write this one a little bit more easy to see here. This is in parametric form. Parametric form. Sometimes we refer to the matrix form as the vector form. That also is another way we can refer to it. And the parametric form is really the scalar form. Just remember, if you were in a situation where you know there's a relationship between y and v, and you knew the y equation, how do you get to velocity from position? Well, yeah, you guessed it. You just take the derivative, and sure enough, if you take the derivative of this top equation, you get exactly the bottom equation. So notice that kind of worked itself out in the mathematics up here, even though we didn't take any derivatives. There's no derivatives involved. It's just kind of baked into the coefficient matrix, the way we set up everything. And last but not least, it says, what can we say about the straight line solutions as t approaches infinity? And so for this one, very last part here, let me see if I can scoot this and squeeze it in just a little bit at the bottom here. We can say that one points along the line v equals negative 2y. That's our lambda 1, right? That's our vector 1. And we know that because it points along this direction, the way we can tell which way along that line on the phase plane is by taking a look at the lambda value. And since lambda up here, lambda of negative 2, that's a negative, we know that it points toward the origin because it's exponential decay. So you can tell just by looking at this idea that this is a negative 1 or negative 2 up here, and this thing right here, this tells us everything I need to know down here. Right? So it's exponential decay, which means it's headed towards the origin. And it's headed towards the origin along this line on the phase plane. And then, of course, the other one, squeezing this in at the bottom of the page here. One points along the slightly less exciting line, v equals y. That's what we did over here. V equals, oh, sorry, not just v equals y, v equals negative y. It's slightly exotic. And because it is also a negative eigenvalue, it points toward the origin. So we can tell a lot just by looking at the eigenvalues and the eigenvectors. So I'll kind of highlight those in a slightly different color. Hopefully this works out well. Got a little dog fur on that one. The negative 1 there, and that stuff there. You can tell it's headed along the line v equals negative y, and it points towards the origin because it's exponential decay again. So this is a lot on one page, I know, but I wanted to kind of encapsulate everything that we did in the kind of the tail end of tail end of chapter 2, where we were able to turn a damped harmonic oscillator's differential equation into a system, and then we now have a way to solve that system even when it's not, partially decoupled. We can solve it by using this eigenvalue eigenvector method, because as soon as you have the eigenvalues and their associated eigenvectors, you can create the general solution. And you can write the general solution either in matrix form or in parametric form. And either way, that tells you an awful lot about what's going on the phase plane. Now, you have access to my Maple files that I've created for this section, and so on that Maple file, I kind of show what's going on here. Unfortunately, I don't have the ability to do both the notes on the screen as well as the Maple file, but that'll get us started. Okay, so that's it for the first video. We'll continue after.